Alright guys, welcome back. Today we're going to start talking about the Bohr model. So we're actually going to start working with what we were talking about last night. Here we have just a quick little image. This doesn't actually show a Bohr model, it just shows the electrons floating in the outside cloud. For sodium, Na, it has 11 protons, here 11 electrons and 12 neutrons. Its electron configuration is 281. That's something we'll start to look at here in a second. So how this works, as we were talking yesterday, the first shell is only going to contain up to 2 electrons, here and here. After that, we move to the next shell, which will contain up to 8 electrons. So we have here, 3, 4, 5, 6, 7, and 8. But together that only makes 10 electrons, and sodium has 11. So we have one more in that third shell. So here we go. We're going to move on to another problem, and I'm going to have you guys identify its atomic number, its protons, its neutrons, and its electrons. Alright, so from this atomic number, you are actually able to identify it, again, by its number of protons, which were given right here. So protons, we had 8. So its atomic number is 8. The number of protons are 8. Our number of neutrons are 8. And then our number of electrons we just add up. So we have 2, 4, 6, and 8 also, which this makes sense since our number of protons and neutrons are equal. We have a stable element, and this is actually an element of oxygen. What? Trying a different way of working with it today, so we'll see how it goes. Alright, so our next slide. What element is this? Can you find its atomic number, its protons, neutrons, and electrons? I'll give you just a minute to go through it. Alright, so let's go through this. So its atomic number is again based off of our protons. Here we have 1, 2, and 3 protons in our nucleus. So its atomic number is going to be 3. Our protons, same as the atomic number, so again 3. Our neutrons, right here in the very center of our atom, that is also 3. And then our electrons, making again a stable element, are noticed by the yellow, which is also 3. This is elemental lithium, also known as Li. Alright, so jumping back to a little bit what we were talking about yesterday, we were talking about physical versus chemical changes. Physical and chemical changes have specific properties. Let's bring these up here. So for our physical properties, so things that are going to help us with a physical change are anything that changes size, shape, texture, color, odor, hardness, and conductivity. So heat, electrical, melting point, boiling point, freezing point, these are all going to be our physical properties. A physical change is actually described as a change in a physical property without changing the substance. So we're not getting a new element. When we burn something, we would create carbon dioxide. that gas we were seeing during our experiment. From here, we're not seeing that, so that is a physical change. Chemical properties. So chemical properties describes how a substance acts when it combines with other substances. So fizzing, precipitates, explosions, heat, released, and then finally a color change. These are all chemical properties that we would see happening or occurring. So a chemical change is going to produce matter with different properties. So we might create a new gas, which would be our carbon dioxide when we were doing our flame. We might create a new substance, our precipitate. Sometimes when you mix chemicals together, you will have a chemical at the very bottom of your flask. So you mix a couple things in together. You may even mix two liquids, and then at the end you have all this solid, these little solid particles down at the bottom. And that is what a precipitate is. So that is something that is going to come out. So that's our precipitate. For us, digesting food is a form of a chemical change, and that's really where we're going to start moving, is into digestion. Iron rusting is a chemical change, which a couple of you guys were talking about in class about hand warmers. Silver tarnishing, copper, it oxidizes, so it starts to lose electrons. And then burning wood, of course, because we are creating that byproduct of carbon dioxide. All right, and also if you need a little additional assistance on these, you can actually go ahead and visit these YouTube videos right here and right here. These will actually show you a little bit more about chemical and physical properties so that you have the option of knowing just a little more in-depth material. And as just a fun little physical change, I added in the scene from Frozen. We have Olaf here. Winter is a good time to stay and cuddle, but put me in summer and I'll be a happy snowman. Playing on the idea of the physical change that would occur when he is in the sunlight. All right, chemical compounds. Let's bring these up. Oops. So a chemical compound is a pure substance made up of two atoms of two or more elements. So here we have a chemical compound. The black here stands for carbon, and our two red on the side are our oxygen. So we have two or more pure elements. We have pure elements of oxygen and pure elements of carbon, and they have bonded together to form a chemical compound. So each of these have fixed proportions of each kind of atom, so there's only a specific amount of oxygen that are able to bond with this carbon. So for example, H2O needs 2 hydrogen and 1 oxygen. Sodium chloride needs 1 sodium and 1 chlorine. If you add another chlorine to this sodium on the other side, it won't bond. And this will get into our discussion about valence electrons, which we'll come up to here in the next little part. So physical and chemical properties differ from elements that compose it. So carbon is going to need 4 bonds right here. Sorry. Sodium is only going to need 1. It's only going to need the 1 bond along with the chlorine. Oxygen prefers to have 2 bonds, which you can see here. It's making 2 bonds to each of these carbons. Most atoms are not stable alone, so they're going to combine with others to become stable. The only ones that are actually stable on their own are our noble gases, which again, those were located on the far right side of our periodic table. Other elements are going to try to combine together to make sure that they fill their outer energy level and they obtain that octet rule. So molecules. A molecule is the simplest part of a substance that remains all properties of the substance and can exist in a free state. So we have some examples of H2, which is actually called a diatom, because hydrogen, it can't be on its own by itself. It has to be paired with at least another hydrogen, otherwise it is considered unstable. We have water, H2O, and then we have glucose, which is C6H12O6. All right, so chemical formula or molecular formula. So let's bring these down. All right, so our chemical formula or our molecular formula show kinds and proportions of elements. These are usually written as we would write H2O. Many of you have heard H2O before. So what we have here is H2O, 2 hydrogens, 1 oxygen, that is water. As I was talking earlier, glucose is C6H12O6, and we write it in that form, the C6H12O6. Where our structural formulas are diagrams showing the kind and proportions of atoms and how the atoms are connected. So it's going to show the actual bonding between them, and we do this bonding by showing lines. Right here we have our oxygen, and it is bonded to our hydrogen with one nice little bond right here. Inside each of these bonds are actually 2 electrons because they are sharing them. So hydrogen has 1 and oxygen has 1 it's sharing. So in there they each have 2. So they can use it from each other. So these structural formulas are pictures or sketches of the molecule, and they're used to let us know how a molecule might actually interact with one another and how they would actually set themselves up in case we decided or we were wanting to actually try to combine molecules. We could find locations on the molecule, like right here. We have our structural formula for glucose. If we wanted to actually add on another molecule or try to combine it, we could find areas where parts were still unhappy or unstable, like this oxygen. It actually still has a couple locations that could be bonded with if we wanted to. We could break these bonds with our carbons, get rid of a hydrogen, and we could go ahead and actually continue on with these molecules. So there are different types of bonds. Let me bring them up here. So the different types of bonds that we're going to focus on first are our covalent bonds and our ionic bonds. So our covalent bonds are 2 atoms sharing 1 or more pair of electrons. And the key word here is sharing. Kind of highlight that because it's a back and forth. They are equally using them about the same amount of time. So a single 1 pair electron is shared, or in a double bond, 2 pairs of electrons are shared. So here in our little picture of water, we have these 2 electrons are being shared between oxygen and hydrogen. In a case where we would have a triple bond, you'll usually only see those with carbon bonds. Every now and then you'll see a carbon in the structural formula written like this. That is showing a triple bond, and they are actually sharing 3 pairs of electrons, so a total of 6 electrons between the 2 of them. 6E minus. E minus, again, is just the expression for an electron. Ionic bonds are a transfer of electrons from one atom to another. An ion is an atom or a molecule with an electrical charge. This electrical charge is due to the gain or a loss of an electron. So as we gain more electrons, the object will become more negative. As we lose electrons, it becomes more positive. So sodium has a plus, because it is low on electrons. That's why it would prefer to bond with a chlorine, which is right next to it, right here, because it's negative. Once those two are able to meet, this molecule becomes stable and unreactive. Aluminum is a 3+. It would actually prefer to make 3 bonds, 3 more connections, where oxygen is O2-, and it would actually prefer to make 2 bonds. So attraction of oppositely charged ions form ionic bonds. Ionic bonds are usually not as shared as easily. They can be more taken forcefully, but it's still just a sharing, or there's this mixture between the two of the using of the same electron. And again, we have here the my name is bond, ionic bond, taken, not shared. And the reason is because they more forcibly pull it. Anything on that the far right side of the periodic table, that's not the noble gases. So over here we have 2 rows. Those are our noble gases right in here. There's one more row that falls right along the side, and they all have 7 electrons. So they only need 1 more electron to fill their outer shell. So they are going to steal an electron from anybody they can. So this is the reason chlorine steals that extra electron from sodium, so that it can be happy, it can fill its octet. And then an ionic compound is going to be neutral, which we saw with sodium and chlorine. Once they bond together, the positive and negative cancel each other out, and we become a neutral compound. All right, on this slide you can see a sharing through a covalent bonds. We have hydrogen atoms, and this is the reason they want to be, they are considered a diatom, is because they need to be with each other to fill their first level. They're only going to fill the first level because they only need 1 more to make that shell happy. So they need 2 in that first level, and then the second one was 8. Here we have some fluorine, F2. Again, they are going to try to share with each other. We have oxygen and carbon. Carbon is going to want to share 4. It's going to need another 4 because right now it only has 4. So if it shares 4 more, it is actually able to make itself happy. So here it's able to gain 2 from the oxygen, and here it's able to gain 2 from the other oxygen, making 8, making it happy. Fluorine and carbon. Carbon again still needs 4 connections, or 4 of these shared electrons, where fluorine only needs 1. So each time carbon makes a connection with fluorine, it makes 1 fluorine happy, and the others, so it needs to find others for it to bond with. So it takes 4 fluorine to make carbon happy, or neutral. All right, so on this page we're going to start talking about, again, about ionic bonds and valence electrons. So atoms that loses electrons becomes positively charged. A way to remember these two is an oil rig. So oxidation is loss. So if we lose an electron, we are oxidizing, and you think of it as, circle it right here, this X kind of looks like a positive symbol. So that oxidizing, we lose an electron, we become positive. When an atom gains an electron, has a negative charged ion. So reduction is the gain. So we reduce, we become more negative when we gain electrons. So you can think of it as reduce, we get more negative. An example would be a sodium atom easily loses one valence electron and becomes a sodium ion. So if the chlorine were to break off from it, it becomes sodium plus because we lose that extra negative electron. A chlorine atom easily gains an electron from sodium and becomes a chloride ion. So now that they have broken apart, the chlorine has its extra electron still, and that makes it negative. So again, extra electrons, so extra negative makes you negative. Taking that negative away makes you positive. Here we are, we have some more covalent and ionic bonds. So we have sharing of electron right here versus our transfer, more of a stealing of the electron in our ionic bonds. All right, so we're going to run through these last few real quick. So van der Waals forces, atoms have different structures, so different elements do not all have the same ability to attract electrons. Some atoms have a stronger attraction for electrons than do other atoms. Atoms in a covalent bond share electrons. The sharing is not always equal, and then even when the sharing is equal, the rapid movement of electrons can create regions on a molecule that have a tiny positive or negative charge. Just kind of run through these last couple slides. So when molecules are close together, a slight attraction can develop between the oppositely charged regions of the nearby molecules, which will result in our van der Waals forces. The intermolecular force of attraction. So this is just an attraction between the molecules themselves. It's not as strong as an ionic bond or a covalent bond. They can't hold molecules together, especially when the molecules are large. So the larger the molecule, the larger the attraction. We have a little Darth Vader over there showing the force. Van der Waals forces are a special part for the tokay gecko because they have tiny hair-like projections on their feet. This attraction of these hairs between a wall or a ceiling allows the gecko to climb up. So they're actually climbing the wall based off of these van der Waals forces that they have. So that